Hi, my name is Liz Thompson. This is a video for IME 315 Financial Decision Making for Engineers at Cal Poly San Luis Obispo. This video is a second example on calculating material costs. So this is in the area of cost of products when we look at the 5 topics we're covering in IME 315. Again, the point here is we're trying to calculate fully allocated costs, which is made up of labor, materials, and overhead. This video is looking at material calculations particularly, and what we have been doing is looking at the cost per unit, and then also the quantity that's used to make the materials. So we use this equation, M is equal to R minus V over N, and defined there as we talked about in the previous video. But this particular example uses a different process, which is that there's a part and it's made up of multiple other parts that are assembled into a larger item. So we're calling this a gadget, and it's made up of widgets, somethings, and fasteners, and you can see the quantity and then the cost per part. So the question now is, what's the material cost for a gadget? So it's actually not that hard to do. We can just add that all up to get what is the material cost, if we ignore the process that there's no defects in this particular process. So it's easy enough just to assume that a batch is one gadget. So remember, that was an important decision we need to make in order to calculate this. So we're going to say we're going to make one gadget at a time, and the calculations then include, because there's no defects, so one time we're making it, we're going to make one good part. So really put V at 0 and N at 1 just means that all we have to do is calculate R. And R is made up of 3 widgets at 201 and 1 something at $3 and 4 fasteners at 50 cents each. And so you can see when we do that particular calculation all the way through, we just add up all those items, and it means that it's going to cost $11.03 per unit. It's pretty logical when we look at it this way. But if in the case of what if we have defects associated with it? So in this case, we have 1 in every 50 widgets are bad and must be scrapped. 1 in every 25 somethings are bad and must be scrapped. And the bad parts can be identified before assembly, and the fasteners are never bad. So now we have scrap rates associated with this. So 1 in 50 is a 2% scrap rate for widgets, and 1 in 25 is a 4% scrap rate for some things. And we'll just need to include that in the calculation. So we change the calculation slightly. So you can see I've added on here the scrap rates in the right-hand column. And so when we do the calculations, which we're going to use the equation M is equal to R minus V over N. In this case, there's no recycling, so we don't have to worry about V, but we do need to worry about N, meaning that once in a while there's bad parts, so we don't get a full part out of each one. And the way we do that is we do the same calculation we did before, where we take 3 widgets and we multiply the cost per widget at 10201. That's the R value. Again, V is 0, and N is 0.98. So on average, we start with 1 good part, but once in a while, 1 in every 50, we have a bad part. And so we've paid for the good part, but we only get 0.98 good parts out. So that changes the calculation for each of these. So you can see some things was also adjusted by dividing by 0.96. But fasteners, we didn't have to do that because there's no defects in that. So the total M value is now 1128. If we remember before, we had 11.03, so now we've increased this to 11.28. It increases the cost per unit because of the poor quality. And the dollar per unit, we're going to just have to add that up because we can detect them before assembly. Now, if you have to detect them after assembly, you need to think through, well, what's the probability of the whole thing being bad? And that's a different calculation. So now let's look at, we have to, not only are there defects, but there's going to be recycling. So only the widgets can be recycled, and they're recycled at $10 per 100. So we'll gather 100 together, and then we'll give them to this supplier, and they'll give us $10 back. So we need to then include that into the calculation. So let's look at V. So V is $10 per 100 widgets, or 10 cents per widget, right? So we just did that simple calculation. And because we're using 1 unit, that would be an important thing for us. So if there's 100 widgets, so let's just pretend, let's look at this difference associated with the batch size. So if we have 100 widgets, then two of them will be recycled. So that's associated with the scrap rate. 2 in 100, which is 1 in 50, will be recycled. And so that means the recycling revenue, if we had a batch of 100, would be 20 cents. So if there was 50 widgets in a batch, it would be 1 that would be bad, right? Because it's 1 in 50, as we've defined here, and that would be 10 cents. But if there's 1 widget, then 0.02, so that's where we get the 2% would be recycled. So then the recycling revenue is 0.02 times 10 cents, which is how much we get it recycled for. So this is 0.2 of a cent, or 0.002 of a dollar. So we're defining our units, our batches, as 1 unit. So we need to use this number for the calculation of the V value. So 1 batch. So in this case, we we have 3 widgets. That's where we have this number, and we subtract out 3 recycling revenues, and we divide it by 0.98. That will get us the cost per unit. So now it's gone down again and now it's 11.27. And so you can see this is a little bit different than the previous example, but one of the main things is you need to make sure you define what your batch size is. And decrease because we're recycling, because we're getting revenue from recycling. So again, this video talks about costs of products, particularly material costs, and it's a second example in that system.